Willkommen.
I'll change to English so it will be easier to understand me. Welcome to this discussion about my theory of relativity. I became interested in the nature of time while watching trains pass by in my homeland. It seemed to me that if a description of the motion of a train depends on the frame of reference of the observer, why shouldn't a description of the time elapsed also depend on the frame of reference of the observer? We have known for several hundred years that a moving observer will describe things differently than a stationary observer. This was first described by Galileo. Suppose we watch a train as it passes by the station and we observe that the train is traveling forward at 20 meters per second. Now suppose that a passenger on the train is walking forward at a speed of 5 meters per second relative to the train. If we watch for 1 second, we will see the train move forward 20 meters and the passenger will move an additional 5 meters towards the front of the train. From our frame of reference, a passenger traveled a total of 25 meters forward. From the passenger's frame of reference, we traveled 25 meters backwards. And from the train's frame of reference, the passenger traveled forward 5 meters and we traveled backwards 20 meters. Clearly, the distance traveled and the direction of motion depends on the frame of reference of the observer. We can say that motion through space is relative. Albert Michelson and Edward Morley performed an experiment in the United States designed to detect changes in the speed of light from different frames of reference. The result of the experiment was unexpected. With great precision, they were not able to detect a change in the speed of light. Since the experiment forced light to travel different distances and its speed did not change, we can only conclude that the light also traveled for different amounts of time. We can therefore say that measurements of time also depend on the frame of reference of the observer. This led me to combine the concepts of space and time together. Since both are relative to the observer, let's think of them as parts of a new quantity called space-time. This is the key to my theory. Space and time behave the same way. This is a brand new idea and it goes against our everyday observations. It turns out that to see the relativity of time, we must be traveling at speeds close to the speed of light. Nevertheless, the effects do exist. The best way to explain the relativity of time is as follows. The more we travel through space, the less we travel through time. More space travel means we must go at faster speeds. When we do this, we find that we measure less time for an event to occur than someone who sees the event occurring in one place. We'll discuss this in more detail in later visits. For now, here's a summary of the important ideas. Measurements of travel through space and through time are both relative to the observer. Space and time can be combined to form space-time. And finally, the more we travel through space, the less we travel through time. That is enough for right now. I'll visit again in the upcoming units. Goodbye, or as we say in German,
Auf Wiedersehen.